So, welcome back everyone. We are talking about studying topological phases of matter, and we are in the first chapter or week 1, in which we are studying the mathematical foundations of geometry and topology. And as I alluded in the first class, we are going a little faster than we generally should. The reason being, this is a very heavy mathematical thing and we just need few concepts from here. And we started with set, which we also assume that you know, and now we were going to put structure and get different things. So, a set does not have anything about its elements. Now, once we give something about how the elements are related to each other and all, this is where we are going to give a new names. And we know that a vector space in which we have a closure property with respect to addition between the elements and scalar multiplication, and we will also go through quickly the closure property of group composition, about compositions of different elements which gives you group. This is what you know. Then we will talk about a topology, which is roughly speaking giving a rule about how to arrange different elements to get a certain shape, and then we will classify different shapes. So, giving such a rule called topology into a set gives us a topological space. And then if we can define some local coordinates, and I will be more sharp later about what these coordinates mean. It is not really coordinate, but roughly speaking a coordinate, which means we can actually take an abstract space and map it to R d, d being the dimensions, a real number, which we will do it locally called chart, and once we can do that, a topological space becomes manifold or topological manifold. And then on every points on a manifold, we can add additional space like vector space or group or Hilbert space and things like that, and the entire thing will call bundles. Okay. So, this is how we start from set, adding structure, get to different things, and for everything one should be able to define a specified map which can take from group to group, and another map vector space to space, and the similar thing one should be able to do from topological space to topological space, manifolds to another manifold, bundles to another bundle. Okay. That is how we will also give the new names for each such map. So, again vector space is something you must have studied in math methods. So, it is made of 3 things, it is written as 3 things. One is set V equate with an addition, vector addition and scalar multiplication, which must satisfy these axioms, or the vector multiplications, vector additions and scalar multiplications are defined like this. You take 2 elements of the set and we add them, and this is kind of an abstract way to denote it. You take 2 such elements, 2 sets, same set, and we get back an elements in the same set. So, element wise we rather denote it this way. So, this is some addition that we have to define based on the set. If it is a vector, then you have the vector additions, and there is a rule for vector additions and so on. 2 elements if you add, you get a new element which also should be part of the same vector space. Okay. Then we multiply with some number, kind of scalar number, to each element, we will get a new element that also must be part of the same vector space, and we denote like this element wise. So, lambda is a scalar number, and with this multiplication symbol multiplied with an element of this vector space, we get a new vector lambda v, and that must be part of this vector space. Alright. So, you can go back and look into all the axioms. I will just remind you a couple of them. So, for example, the vector additions must be commutative, associative, and the one which are sort of more relevant for most of our discussions later are that they should also have the identity element and an inverse. So, identity elements must be a element of the vector space such that if you add to vector if you add that element with every elements of that vector space, you get back the same vector. That is we sort of denote it by 0. Okay. And the inverse then has to be will be defined with respect to what is the identity element here, and in this case that is 0. So, the inverse element is here we are denoting it by minus v. So, that if you add them, the addition should be vector addition, you get back that identity element. And so, scalar multiplication will also have similar axioms which we do not need, it is just a kind of reminder. And then again you start with some set and you have a group composition, a binary operation, and together we will call this set a group if it follows these axioms. These axioms are sort of denote this group compositions means you take two elements, two different elements or different elements of this group, and then you get back a new element which also has to be part of this. So, these are all closure properties, okay. And we just talked about that, and it has to be associative, and also you need to have an identity and inverse sort of pretty much defined, and they are sort of denoted this way. Here this is the inverse of a group element should give you the identity element, where the identity element with this group composition to every element of that group should give you back the same element. Okay. So, this is different from vector space because it does not have the scalar multiplications and few other properties. And there are many types of groups, and we will not have time to talk about every one of them, but the one we will essentially be needing are these symmetric groups. So, generally speaking the groups will be two types. One is continuous group. So, all the elements are sort of continuously varying from the other elements. For example, the translation, right. If I take any points in the positions in which some particle and some equations are defined, and if you translate it infinitesimally small or even large distance and redefine the equation of motions, if things remain same, then we know we call it a translational symmetry, and all elements of that symmetry forms a group called continuous group. Okay. Compact group, for example, if you have rotations, so rotations are defined by 2 pi, or even the periodic boundary conditions are defined by translation by discrete vector and so on. And those things also form a group. You have orthogonal group, you have unitary group, special unitary group, and so on and so forth. Okay. Whereas the discrete group will be you are pretty much doing these things, but not continuously, but only discrete things, right. So, for example, Z, all the real numbers forms an infinite group. Discrete lattice translation gives you group which is kind of a discrete translation by a fixed length A, and if the theory remains invariant, that is a discrete translational symmetry, and the elements of that group is called symmetric group, and it is an infinite number. You can translate all the way to infinity. Whereas the finite one will be, for example, the discrete rotations. Okay, so many of these lattice has discrete rotations, like square lattice you can rotate by 90 degree and everything remains same, and then 120 degree and 180 degree and so on. So, that is the discrete rotations. Inversion, you go backward, then if your theory remains invariant, that is an inversion symmetry. I am pretty much focusing on the symmetry group because that is what we will be needing. And mirror, You put a mirror, and if everything remains same, that is also, and the elements of those groups will be then just a mirror reflections, right. If mirror is along the yz plane, then you only take the x and make it to minus x. So, there is only one element of the group, which is or two elements including identity and inverse, so maybe 3 elements. So, you will have just x goes to minus x will be the element of this group. So, these are finite group. All right. So, that gives us the quick reminder of what set is, what map is, what vector space and group are, and how they are sort of defined by adding structure into set. And the reason I also did that, because now we are going to add a new structure to the set and going to define topological space and continuous map and homeomorphism. All right. So, this is a slightly more abstract definition, much less intuitive, but let me start with an intuition, which will be not a complete mathematical definition, but it is always good to start with some sort of a physical picture to get an understanding of what this complicated abstract mathematics are telling us. So, as I said, set does not have any sort of structure among those elements, right. You can just arrange them any way, you can grind them, and you can sort of place here and there and so on, and nothing really changes, and you can take a few elements out of it. It just the set gets reduced, but it does not say anything more than that. It still remains a set with maybe few number of elements. But now that is not so much helpful for our for defining mathematical rules, and that is not how the inverse is also pretty much defined. The reason being, when a kind of a bird is flying from one tree to another tree, it sort of flies through a space in which there is some sort of a continuity. Bird cannot just fly up to certain point, disappear and reappear somewhere else, right. So, it is actually flying in a space in which there is some sense of a continuity, and if that space the bird can continuously fly from one to another, that is one way of going from one tree to another. But now let us say imagine that there is some sort of a barrier between one tree to another tree, and then the bird has to fly around it or under it or outside it. So, some points of the space has to be removed, which belongs to the wall that the bird cannot go. So, then it has to overtake it. So, then you also have to tell that rule, and that rule also dictates how the bird can flow, and the vice versa. How the bird has flown, whether it has seen an obstruct and has to turn around or go in a different way versus if it could go all the way. So, that will tell us about what sort of space that these two trees are lying and how the bird can flow among them. And that is how the particles, the electrons and all these things are their equation of motions in atoms, in lattice and all, and how the electrons can move around and what sort of a underlying space it undergoes, what sort of space the Brillouin zone or unit cell offers for these particles to move, and if there is anything that breaks the continuity or that anything that bends the particles because of some curvature in the space and all, and that is topology roughly speaking. And how do you sort of do is that we sort of give a rule about how the nearby points are related to each other, and that is a rule we give, right. For example, when we build some shape, I could give the raw materials, which could be some point particles and all, some sand, and then I can ask you to build something, and then you can probably build many things and all, but that does not really, I have not given you any topology to build only certain shape. Rather, if I give you Lego pieces, and Lego pieces are kind of our topology, I am giving you certain rules about how all these small microplastic pieces are put together to get a smaller shape, and with that shape now you can build a bigger shape, and you can only build few shapes with a given set of Lego pieces, and that is how a topology is. So, topology is roughly speaking giving you the small pieces or small Lego pieces to construct bigger shapes. Okay. So, set is all those microplastics and topology is these small shapes which you can now put together and to build bigger the entire set. Okay. So, you can glue together to get different shapes, and then we will learn how to distinguish different shapes and what are the quantifying measure to define different shapes. Okay. So, now we go back to the mathematical definition. It will be less intuitive, and but then we will see, we will give examples. So, a topological space is a pair with set and topology, where X is a set and T x is a collection of open subsets like this. These are the open subsets, right, and this so it is a collection of open subsets which we denote like this. So, it itself is a set, the collection of open subsets where tau's are open subsets and I is the index. So, how many topology we give? I can give you n number of Lego pieces, I can give you n plus 1 and n minus 1 and so on and so forth. So, that gives you the index. So, how many topology we have given? It is not that anything you give will qualify for a topology and then anything you give will help us make glue together and get a shape. So, there has to be some axioms, and these are the axioms. So, it should contain an empty set. Okay. And any arbitrary union of this open subset, any arbitrary union, I can take 2 of them, I can take 3 of them, or I can take all of them and so on and so forth, and I should be able to get another open set. That should also be part of the topology. And every arbitrary intersection of the open set should also be part of the topology. I take this one and I remove some part which belongs to this, and the remaining one should also correspond to another open set. And obviously, the empty set is also part of it. So, if the intersections between them gives you does not have any common thing, common elements or common open set, that is also fine, because we have the empty sets defined. So, there are many types of topological space, and there are many types of topological space, but we will not be interested in and correspondingly different types of topology. And what we will rather be interested in for physics, these are the topology that is interested to us, is called standard topology. So, standard topology roughly is what I alluded, is open balls. The topology is made of open balls, and ball, when we said we have in our mind that is a 3D, but it can be defined or any dimensions. So, for example, 2D that will, the open ball will be more of a open disk if you like, and that is what we define. So, R2 is a set of all these real numbers, and I am giving a topology. For every point there is a neighborhood with open. So, that open says subset means I am including all points inside this set, but not the boundary states, boundary elements, and that is how an open set is defined. Okay. So, I can give one or I can give many, and we will see those examples. And when we give an open balls or open disk with certain radius, that is called standard topology, and in physics we use standard topology. Okay. Let us take a few examples and then we will come back to little more about what topology is. Okay. And the examples we will take here are kind of a simpler one, the relevant one. So, for example, we start with R2, which is this R2, this is a set, and I gave R, which is line, and this is open because it goes from minus infinity to plus infinity, and infinity is not well defined, it is not bounded, and that gives a topology. You can actually go back and see that it follows all the axioms, 3 axioms, okay, and including of course the empty state. But then if I give R and S, I can give a circle. Can I build a topology? Can you call it a topology? No, it is not, because the union of them is not included in this topology. So, it violates one of the axioms. So, now for the standard topology, so we give open sets, and as I said, I just have defined the open set is that any points inside a disk or ball is a open set, and once we give such an open set, one or many, that will qualify for a and it's roughly also obvious, right. Once you give many such, then you can glue together and build some shape, and we can define a continuity among all the points, and we can define the shape in which the particle can move from one point to another without sort of being without vanishing somewhere, right. On the other hand, if we include the boundary points of this open set, then it is not a topology by definition, right. It is not a topology because you have also included the points on the boundary. So, that is not an open disk, so it is not open set. And you can give 2 of them. So, if I just give 2 disjoint one, it is not a topology because the union of them is not part of the topology. So, if I want to build a topology, I have to, with 2 open sets, I have to give 2 of them and also their union. Okay. All right. So, we will take more examples, but let us talk about some a map that can take us from one topological space to another topological space, okay. And it is called continuous map. So, what does it do? So, it is again a map, takes from. So, topology is defined by 2 things, one is the set and the topology, and I have another space y and T y. Now, I have a map which takes from set x to y is said to be a continuous map if all points in an open set V of this topology. So, we start with the range set generally for continuous map. So, all points, if you take any points, the pre-image, not necessarily the inverse has to exist, the pre-image of all these points which is defined by this map belongs to an open set of the domain topology or domain set, and that open set, that this F, the pre-image of F takes me to, which is U, must also be belong to this topology. All right. So, roughly speaking, the points from topology to points from the topology, open sets to open sets. Okay. So, roughly speaking, intuitively, it is sort of going from one topological space to another topological space, that gives the structure. And what is the structure? The topology that must preserve the structure. Then that is a valid map from the topology to topology, right. It is not going from just any random set to another set, it has to preserve the structure mapped from to points in the open set in the target topology. All right. And if this is bijective, which is what we will be mainly interested in. So, if I take an open set of a topology of X, all points is mapped to all points in the open set of the topology of the range set. So, if the open set is there, if it is a bijective, then you can also go backward. So, inverse exists, and such a bijective continuous map is called homeomorphism. So, it is a buzzword, it is a morphism, it is homeo because it just takes from topology to topology. Morphism means isomorphism means a map that preserves the structure. Iso means same and morphism means structure. All right. So, then this is the notation. So, if two topology topological space are homeomorphic to each other, or there exists a homeomorphism, continuous map, continuous bijective map, then these two spaces are called homeomorphic, and roughly speaking we will just call them, these two topological spaces are same, in the sense one can continuously deform from one space to another one, and we call this as a isomorphism symbol, and here isomorphism, on top of isomorphism it also preserves the topology. So, it is called homeomorphism. So, one can put that homeomorphism as a subscript. Some books it does, some books it does not do, but it helps us. So, let us say S1 is a topology, is a topological space, and every point in a open set maps to every point here. So, then this is homeomorphic. So, I can put a homeomorphism here, and I can sort of take this ring and kind of wind it, but I do not touch this point, sort of still keep a gap between them, that is also homeomorphic, right. All points are mapped to all points and with the open set. But now if I make a knot, now at this point the open set is not, can be mapped to 2 points, which is moved to 1. So, that is why they are not homeomorphic. So, we have actually changed the topology here, whether this is topology or not we do not know yet, and these are topology, and we learn that this is a topological space of course, but it will not be a manifold, but they are not the same topological space. And then this one in which I have removed some points. So, all these points can be mapped to all the points here, but not all points, because here everything is continuous. So, the open sets that gives the topology can be glued together continuously over the entire thing, but here there is a boundary, okay. There is a sharply cut off here, so you cannot define an open set here, okay. But so, this is not homeomorphic to this, but it is however homeomorphic to R2. So, it is a different topological space, because I can just continuously unwind it and make it R2. This is also topological space as we defined earlier, but they are not homeomorphic to this is not homeomorphic to this. So, all right. So, now let us also take few examples, and the relevant one for condensed matter, about how do we change the topology by adding conditions on the set, okay, or equivalence class, equivalence relation. So, let us start with some R2, which is our 2-dimensional space, and now in the first case what we have done is that along the y direction, let us call it y direction and this is x direction, it does not matter, there is no direction defined yet. Let us just take this is R and this is also Cartesian product with R, and now every point on this point, like this point, I put an equivalence relations to say that this is equal to this. This is a periodic boundary condition, but I have given the periodic boundary condition only along these directions. So, then I can just wrap it and make a cylinder out of it. So, this is not homeomorphic to this, because this one did not have that additional condition. So, everybody is open set, but now these guys are no longer open sets, they are sort of identified. But this is however homeomorphic to cylinder, and cylinder is denoted by R1. At every R1, every point I have a circle, right. This is a Cartesian product. In the second case, I give the boundary condition, but in a reverse way. So, every point here is not equal to this, which was the case here, but equal to this one. So, now if I want to wrap it, I have to give a twist. I take a piece of paper, you can see how this is done on some YouTube video, on how a this is called Mobius strip is defined by giving the periodic boundary condition on R2, in which this point and this point you want to put it together and you have to make a twist, fold the paper and bring it together, so it becomes this. So, this condition has changed the topology, okay, and this is homeomorphic to this, but not homeomorphic to this or this. So, it is a different topological space. The third one is going to give us the 2D Brillouin zone. What we have done is that every point along x direction is identified with every point at the x direction at a distance a, and every point on the y direction is identified with every point on the y directions at a distance b. So, how do you now wrap it? You take this and wrap it here, and then you wrap this one and this one, and what you do is that along this direction you get a circle, and for every point on the circle these points are also circle. So, S1 cross S1, this is my 2D Brillouin zone, and that is identified with torus, sometimes called 2 torus. So, these are homeomorphic. So, now I can see just starting with just a 2-dimensional space, by just giving this periodic boundary condition I made different topological space, and you can see that this topological space has a hole, right, and this one has a twist, and this one also has a hole, but these two are still different. There is no periodic boundary condition along these two. Now, you can even continuously deform, as we often see it in popular science, is that this torus can be continuously deformed to a cup. I can see that topologically the same, because there is also one hole, and but this is not homeomorphic to a cup without a handle, because this one does not have a hole. Now, another sort of a boundary conditions we give to start with R2 and get a S2. How do you do that? You identify all points, not just the sidewise, all these points. So, it is like take and then you put it into one point, then it becomes a circle. So, it is like making a momo. You start with some chapati and you take all points at the boundary and put it together into a point, and you get S2. It is called projective space. Okay. I just give a different periodic condition and change the topology, and these two are however homeomorphic to each other. Now, more relevant topological space for us would be like Fermi surface. So, this is a Fermi surface for some Brillouin zone, and this is a Fermi surface for another Brillouin zone, but as long as the Fermi surface topology is concerned, this one I can continuously deform into this one, and they are this two Fermi surface are homeomorphic. So, many of these underlying properties of these two material, which can be different material and different structure, as long as the properties are coming from Fermi surface, they will be pretty identical. Okay. And again this will also be identical to this, as long as the topology goes. This one will however has a different thing, because here you have sharp edges which will not make it a manifold, and I will come back to this question again during the manifold, or not a differentiable manifold, because you cannot use a differentiations here if it is really sharp. I mean, in practice it is not, but otherwise this is just a different shape which can be continuously deformed to this Fermi surface. Okay, so, they are also homeomorphic. On the other hand, this one has holes. So, some points of the set has been removed. So, these are not homeomorphic. Okay. So, certain properties will change. For example, if you take the quantum oscillations, Subanikov-de-Huspan oscillations, and along the magnetic field you see some structure, it tells you how the Fermi surfaces are perpendicular to the magnetic field, and you will see certain properties will be very similar, but will be here very different, because you have a open circle. Okay. All right. So, now comes to an important question about what is a topological invariant. So, now we have talked about topological space, in which we have started with some set and we gave a topology and we construct different shape, and we are saying that if there exists a continuous map, we can go from one shape to another shape. And now all right, we got two different shape, but what are the properties that are supposed to remain same, and what are the properties that are supposed to remain may change. Okay. The properties that remains invariant are called topological invariant, and those are the invariants which will not depends on the details of the Fermi surface and all, but only depends on whether it is a closed Fermi surface versus open Fermi surface and so on. Okay. So, mathematically topological invariants are any properties, there is no kind of a restrictions on how many topological invariants a topological space can have. It can be many things, including even as simple as dimension. Are any properties of a topological space that remain invariant under homeomorphism, which is continuous deformation or continuous map, which is bijective. Okay. So, this is a weaker notion, and as I said, there is no restriction on how many topological invariant a topological space can have, and also they do not necessarily have to be physical observable. So, mathematicians have many things to define topology, topological invariant, to characterize a topological space for separable, Hausdorff and compactness and dimensions, and we will not go into all of them, but rather we will just focus on the physical properties that one would be able to measure and that quantifies a topological space, and some of them will be like orientability. As we started with a Mobius strip versus a cylinder, they have a different orientability, and let me talk about that. And there will be also things like homotopy group, winding number, Chern number. These are the topological invariant that we can define for a given topological space, and if the winding number changes, then we know that the topological space has changed. All right. So, let us go back to the Mobius strip. So, Mobius strip has a winding, has a kind of a twist somewhere. The twist can be anywhere, but it is there somewhere. So, as we take a right handed coordinate system or a spin, as you go around that, the right handed coordinate system will become left handed coordinate system when it comes back to the same point. Or if I start with a spin and the spin will rotate somewhere, they come back. So, it does not come back to the same vector. So, it has a orientability of 1, it will just come back with the opposite directions, compared to cylinder in which you start with a spin or vector, and as you go around it, it does not change the direction, right. So, it has cylinder has orientability 0, whereas this Mobius strip has orientability 1. So, this is a topological invariant. One also quantifies it in different way, which we will see, but that is how it is. And so, this means that cylinder and Mobius strip also cannot be continuously deformed one into another. So, these are indeed the topological invariant that changes. So, in physics, as a particle moves on a topological space, it acquires some distinct properties which may be related to topological invariants, and those are the properties we will be eventually interested, because those are the things we can measure, and those are the properties that can remain robust as long as the topology remain robust. Fermi surface remains robust, Brillouin zone remains robust. So, it does not depend on any small changes and all, right. And there would be things like Berry phase, winding number, Chern number, etc., which are related to something that we can measure like quantum Hall effect and other observables that we will talk about, right. The question is then, how do we quantify it? Okay. So, we will quantify them in more mathematical sense later, but let us quantify them in a abstract topological space, okay. And we quantify them through how the curves can be drawn on a topological space, and what sort of curve we can draw, and what sort of loops we can draw, and whether those curves and loop form any sort of a group, and then if you change the topological space, whether the group associated group, the homotopy group changes or not. So, these things we will discuss as a possible way to define topological invariants. So, maybe this is a good time to stop for this lecture, and we will come back to define the topological invariant in the next class, and thank you very much for your attention.